Hello, everybody. Welcome back to Math 2415, Calculus 3. Today, we're going to discuss Section 4, cross product. Before we do that, let's recall what the dot product did. The dot product gave us a scalar. Like this u dot v is actually, you take the components, take the product of the components, and then add them together. Or if you're dealing with angles between two vectors, you can look at the magnitudes of vectors u and v times the cosine of whatever angles between them. So that's the important part of that. The cross product now is a different process. For example, here, let's look at, when we look at two-dimension lines, what do you need to have to do two-dimensional lines? You need to have 2 points or 1 point and the slope of that line from 1 point to the next. In 3 dimensions, we now talk about planes or three-dimensional spaces. What we need here is we're dealing with something called a tilt. What we're looking at here is the tilting. How do you find this tilt? Is you multiply 2 vectors in one plane together. Found by multiplying two vectors in the plane to get a third vector. That is perpendicular to the plane. So what we're doing here is we're looking at, we need 2 vectors to be on a plane. So any two-dimensional vectors anywhere. So, and what we have to do is we're going to do the process and then find something that's going to be called normal to it or orthogonal to it. All right. And this is to do that, to do this, we use the vector product, or another name, because we have 2 vectors, we're multiplying together. They could be joined together or they could be separate vectors. Another name for the vector product is called the cross product. The cross product gives us a way to find a variety of geometric quantities, values, since we have 3 dimensions, we can find the volume of an object, the area, if it's a 2-dimension, or we can find the surface area of an object, and we can find perpendicular vectors to a line or a curve. All right, so let's look at the first thing. The cross product of 2 vectors in space. After we're looking here is it remember in algebra we talked about if we have two lines that could either be parallel, that could be the same line, they could be perpendicular to each other, or they could be anything else. So we'll look at if two vectors are perpendicular to each other, there is one point or line in common, depending on how many dimensions you have. If two vectors are parallel, so if two vectors are parallel, then one vector is a non-zero multiple of the other. So they have in algebra we talked about that the same slope but different y-intercepts, and that's all it really is. The difference is the dimensions of them will be the same. It's just that they're going to be some scalar multiple difference of each other. If they're not parallel, they define a line in 2 dimensions or a plane in 3 dimensions. Here, if they're not parallel, the vectors are linear combinations of each other, vectors u and v. What that means, linear combination is we can multiply where a and b are scalars. So we can make linear combinations so that they're each multiplied by some non-zero value. So we select a unit vector, n, that is perpendicular to the plane. It's perpendicular to the plane. How to do that? Remember, by the right-hand rule. If you go that way and you curl your fingers, the thumb is the z-axis and the fingers curl from the x to the y-axis. So it goes from the x-axis to the y-axis, and the z-axis is up and down. How do we do this? How do we do this? choose an n. Remember, n is our normal vectors, to be the unit vector. That points the way your right hand points. When your fingers curl through the angle theta from U to V. So now, okay, now originally the rule of thumb was the X and Y, but now we're looking at from one vector to the other vector. Because when we'll look at one vector to the other vector, we know the normal vector will be going up from that point. All right, so let's define what a cross product is. The definition. The cross product U cross V, that's how it's read, U cross V. It's not multiplied, it's U cross V. Unlike the dot product, which gives a scalar, the cross product gives us a vector. So U cross V is equal to the magnitude of n times the magnitude of V times the sine of the angle between them. All that times a unit vector. We'll say n equals the unit vector. All right. So again, the cross product gives you a vector, the dot product gives you a scalar. The vector U cross V is orthogonal to both U and V because it is a scalar multiple of n. Which is what that unit vector is. Remember what orthogonal means? Orthogonal means perpendicular. Okay, let's look at the properties. Of the cross product. Cross products of two non-zero parallel vectors equals 0. Now, why does it equal 0? Because the sine of theta equals 0 at both 0 and pi. So at our endpoints at 0 and pi. All right, so everything else other than that, our cross product will work. if one or both vectors u and v are zeros, then the cross product is zero. The reason being, if u or v are either of them are zero, then the magnitude zero times anything is zero. Okay. So that's what we're talking about. What we're talking about here is parallel vectors. And non-zero vectors, u and v, are parallel if and only if their cross product is zero. And that's an important concept we're going to be referring to a lot. The properties of the cross product state that one, well, let's find our variables first. Let u, v, and w be non-zero vectors. And R and S are scalars. So our first property, RU cross SV, since these are scalar multiples, we can factor out the scalars. And we have this, the product of the scalars times the cross product. Right. These things go both directions. U cross V plus W. This is similar to what would look like the distributivity, but it's not really distributivity because these are vectors and we're doing the whole process with the cross product. So it's U cross V plus U cross W. So it's U cross V plus U cross W. And you combine those at the end. V cross U, because originally, remember, we always started with U cross V, but if we do it backwards, that's the same thing as U cross V. It's a negative of it. So if you change the juxtapose the vectors inside the equation, it actually changes the sign from positive to negative. The reason for that is because you're now changing directions. So V plus W cross U, it's similar to what we have up here. It's just that, remember, we change the values around. So this is V cross U plus W cross U. So this one's going to be the negative of that, and this one's going to be the negative of U cross W. Zero cross any vector is zero. Remember, it's a product. So the magnitude of zero is zero times anything else becomes zero. U cross V cross W. Now, when we take the cross of a cross. What this happens now is we now have a dot product. So it's a UW dot V minus, since it's UVW is UWV, this one is U dot V dot W. All right, so those are the properties, and we can refer to those. Here's another thing that's important, because now, similar to what we talked about in Rule 3, if I juxtapose the vectors, it changes from positive to negative. Here we have other cross product products. Remember, U is U1, U2, U3. V1, V2, V3, and we put them together. We could also have U1I, U2J, U3K. V1I, V2J, V3K. Now when we look at it this way, we have IJK. I cross J is the same thing as the negative of J cross I. That equals K. Because remember, you're going from I to J, that's K. J cross K, which is the negative of K cross J, is equal to I. And then K cross I is equal to the negative of I cross K is equal to J. So whenever you do cross products or distribute, if you're doing a cross product process, whenever you have an I cross J, it becomes K, and K cross I, and vice versa, all the other ones. I cross I is the same thing as J cross J, same thing as K cross K, those equal 0. I'll try to find an example where we could do this if we do it the long way. Right, the magnitude of U cross V is the area of a parallelogram. Not the dot product, it's the cross product. The magnitude of it gives us the area of the parallelogram. Since n is a unit vector, the magnitude of U cross V is the magnitude of U cross V is equal to the magnitude of U times the magnitude of V, the absolute value of sine theta, absolute value of n. Or just look at it, absolute value of U, magnitude of V times sine of theta. This is the area of the parallelogram defined by U and V. Just remember, for the area, we need base times height. The base is determined by the magnitude of U. The height is the magnitude of V times the sine theta. So area equals base times height equals absolute value of U, magnitude of U, magnitude of V, sine theta. There's your area. So, and this can also be written, since where it came from, it can be written as the magnitude of U cross V. So remember, this came from up here, and that's U cross V. So to find the area of a parallelogram, we could take either of those equations. Now, here's another big difference between the cross product and the dot product. With the cross product, we can convert the vector components into a matrix. So we use the determinant to find U cross V. Yeah, we can determine U cross V from the components of U and V relative to the Cartesian coordinate system. We could do that. How do we do that? By letting U, the vector U equals U1I, U2J, U3K. And vector V, V1I, V2J, V3K. So let's look how to do this now, because using the cross product, we have to combine some of the rules we just talked about a second ago, along with the rules of algebra, like the distributive property. So let's look at this. So we have vector U is U1I, U2J, U3K. Cross vector V is V1I, V2J, V3K. Now, using the distributive property, everything in this first parentheses will get multiplied to everything in the second. Now, this is where it gets long and drawn out, but I'm going to show how it relates to those cross product rules. So U1I times V1I. We got U1 times V1, I cross I. That's the first one. Plus U1 times V2, that's I cross J. U1 times V3 I cross K. That's the first one gone. Plus now the second one. U2 times V1, that's J cross I. U2 times V2, J cross J. U2 times V3, J cross K. That's the second one gone. Now U3 times V1, K cross I. U3 times V2, K cross J. U3, V3, K cross K. All right, so we just use the distributive properties there. Now, one thing to remember is I cross I is 0, or anything. So that's going to be 0. That's going to be 0. That's going to be 0. Those are gone. Let me see, where's that chart? So I cross J is the same thing as K. So this one here becomes K. I cross K is the negative J, so it's negative J. J cross I is the negative K. So this one's negative K. J cross K is I. K cross I is J. And K cross J is the negative of I. So now we have U1 V2K just minus U1 V3J. It's minus U2 V1K plus U2 V3I plus U3 V1J minus U3 V2I. So we have 2 of each. Let's combine them. So the I's, we have U2 V3 minus U3 V2I plus, let's think of the J's. We have U3 V1 minus U1 V3J plus U1 V2 minus U2 V1K. Okay. Here's a good test to see if you're doing it right. For the I's, remember I is the first one, so we can't have any ones inside here. So it's 2, 3, 3, 2. J is the second one, so we can't have any 2s. 3, 1, 1, 3. K is the third one, so we have only 1s and 2s. 1, 2, 2, 1. All right, so that is our cross product. If you have the components, you can multiply the U2 times V3 and then subtract it, and then that'll be your coefficient for the I component. You can do it that way. That's one way of doing it. Another way is by using determinants of a 2 by 2 or 3 by 3 matrix. All depends on how many data sets you have. We'll use the same information here. And you say that U is made up of U1I, U2J, U3K. V is V1I, V2J, V3K. So when we do the cross product, we have to take this information and put it into a 3 by 3 matrix. The top row are the indices I, J, K. That's research. So now under the I, you have the U. So we have U1, U2, U3. And the last one is V1, V2, V3. Actually, it really doesn't matter on how you put these lines and matrices because it'll give you the same answer no matter how you look at it. But once you do it this way. And then from there, you find the determinant. Okay, the book likes using the sub matrices for I, but I don't like doing that. I'll show you the way I like to do it. It's much faster. So let's look at an example. Okay, given U is 2I, 1J, 1K, and V is negative 4I, 3J, and 1K. Find the two different cross products. So A, we're going to find U cross V. So it's I, J, K. Now U is made up of 2, 1, and 1. Only put the coefficients in there. And the V is made up of negative 4, 3, and 1. And we're looking for the determinant. So the way I like to do it, I put the matrix again down here. I repeat the first two columns. So I repeat the first two columns over there. Now, I do diagonals. Those diagonals I add to each other. So I have 1, and this is the product of each of those. So 1 times 1 is 1. So I have 1I plus 1 times negative 4 is negative 4J. 2 times 3 is 6K, so it's plus 6K. Now, and we do the opposite way. These three diagonals, we subtract. So again, 2 times 1 is 2J. 1 times 3 is 3, so it's minus 3i minus negative 4k. So these ways are positive, these ways are minus. So we have I minus 4j plus 6k minus 2j minus 3i, negative, negative makes it positive. So combine all those. How many i's do we have? 1 minus 3 is negative 2i. Negative 2, negative 4 makes it negative 6j. And then 6 plus 4 is 10k. So for u cross v, our resulting vector is negative 2i minus 6j plus 10k. To find b, v cross u. Well, remember the rules we had earlier, the properties. Since we reversed them, this is actually the negative of u cross v. So we take the negative of negative 2i minus 6j plus 10k, which makes it positive 2i, positive 6j minus 10k. That's v cross u. That's all there is to that. But yeah, that's much faster, much cleaner than the other method. All right, let's look at another example. Given the vertices of a plane, P, Q, and R, find the vector perpendicular to the plane PQR. Remember I said earlier, we have three vectors, three vertices on a plane. If we could draw the picture, but my picture is gonna be horrible. So, but we have to find two vectors on this plane. So let's find PQ and PR. Remember how we find this? So the first one we do from P, 1, negative 1, 0 to Q, 2, 1, negative 1. So it's going to be 2 minus 1 I, 1 minus negative 1 J, negative 1 minus 0 K. This becomes I, this plus, so it's plus 2J minus K. All right, so that's the first vertex. I'm not a vector. So I'm going from P to Q. Now I'm going to go from P to R. P is 1, negative 1, 0. R is negative 1, 1, 2. So since starting at P going to R, it's the second point minus first. So it's negative 1 minus 1, 1 minus negative 1, 2 minus 0. 1 minus 1 is negative 2i. 1, negative, negative, positive, so it's plus 2j. 2 minus 0 is 2k. Okay, so now we got to find the cross product of those because we want to find vector perpendicular. We have the two vectors. Let's call this u and call this v. So we need to do u cross v. So I, j, k. The vector u, the coefficients only, is 1, 2, negative 1. And for v, negative 2, 2, 2. I, j, k, 1, negative 2, 2, 2, negative 1, 2. Repeat the first two columns. And just do diagonals. Two times 2 is 4. I. Negative, negative is positive. 2 times 1 is 2j. So it's plus 2j. Remember, all these we add. 1 times 2 is 2. Okay. Now all these other ones, the backwards ones, we subtract. 2 times 1 is 2j. So it's 2j minus 2 times negative 1 is negative 2i. Negative 2 times, so minus negative 2 times 2 is negative 4k. 4i plus 2j plus 2k minus 2j plus 2i, those plus 4k. 4i minus 4i plus 2i is 6i. 2j minus 2j cancel. 4 plus 2 is 6k. So that's the vector perpendicular to that curve. Right? Another example. Find a unit vector perpendicular to the plane P1, to that plane, this plane, and that plane. It's a plane of, so these are three vertices. So we'll do the same thing. So since PQ cross PR, like we just figured out, is perpendicular to the plane, its direction n is a unit vector perpendicular to the plane. So we have to find the unit vector. So the unit vector is perpendicular to the plane, which means n is equal to PQ cross PR over the magnitude of PQ cross PR. So the first thing we have to do is find PQ and PR. Okay. That's the same as we found last time. That was what we had from our previous example, same points. So we have the cross product. So 6i plus 6k. And the magnitude, remember, is this square root of 6 squared plus 6 squared equals 6i plus 6k, 36 plus 36, 6i plus 6k, square root of 72. Square root of 72 is 36 times 2, so it's 6i plus 6k. So this is 36 times 2, which is 6 square root of 2. So square root of 72 is 36 times 2, square root of 36 times square root of 2, 6 square root of 2. Split those up. 6's cancel, so our n is I over square root of 2 plus k over square root of 2, which you wanted to square root of 2 I over 2 square root of 2k over 2, however you want to put it. Be very, very careful also. So whenever we're finding determinants, and finding determinants, write v in the component form. v1i, v2j, v3k, not as v1, v2, v3, because you need to have, for the matrix, you have the columns of ijk. One of the uses for the cross product is to determine torque, or a torque vector. What is a torque vector? If you had a screw and then you put a wrench over it, if you're trying to loosen it, you're going to put a counterclash. Torque is the force, distance, and direction of where you're pushing this wrench to take off this bolt. Okay, so that's what we're looking at here. The torque vector points in the direction of the axis of the bolt. Okay, so the direction of the axis of the bolt, according using the right hand rule. So as we're saying, it's counterclockwise. So that's the torque. The bolt is our y-axis. So our fingers are going that way. So we're going counterclockwise. So this is going from X to Y. So that's what the torque vector is. The magnitude of the torque. Depends on how far out on the wrench the force F is being applied. One, how far it's going apart, and two, how much force F is perpendicular to the wrench. At the point of application. So where you're holding it. You know, all that's saying there is the longer your wrench, the greater the magnitude of the torque. That's why if you ever try to take off a lug nut from a car, if you have a lug wrench and it's still not working, put an extension pipe on there. The longer it is, it takes less force to open it, undo that bolt. So the torque magnitude equals the length of the lever arm, call it R, times the scalar component of the force F perpendicular to R. So that's where the torque magnitude is. With this mathematically now, what we're looking at here is we have the magnitude of R times the magnitude of the force. Since we're going vertically up and down, it's our rotation. So the torque magnitude so what this really tells us is a cross product between the length of the lever arm across the force. Like earlier, if n is a unit vector, along the axis of the bolt in the direction of the torque, then we get this formula. We get R cross F is equal to magnitude of R times the magnitude of F, the sine of our theta times N, which is our torque magnitude. Okay, now what this is really saying now, our torque, it has to be perpendicular. Since the bolt's coming out, our rotation has to be horizontal. So if this is our bolt, our torque has to be horizontal. If not, then we have no force acting upon it. So in other words, you can't unscrew something by pushing on it. And remember, the cross product, if it equals 0, that means the vectors are perpendicular. All right, let's look at an example here. Find the magnitude of the torque generated by the force F at the pivot point shown below. So we have force of PQ the force is acting. So that's a pivot point, but it's PQ. That's the whole objective there. It's pushing down. So we go from PQ to F. We want the magnitude of it. So that equals the magnitude of PQ, the magnitude of F times the sine of theta. So the magnitude of PQ is 3 foot-bars. The force acting upon it is 20 pounds. And the angle acting upon it is 70 degrees. 3 times 20 is 60. Sine of 70, 0.94, 56.4 foot-pounds. All right, that does it for section 4. I hope it helped. All right, let's get ready to number 5.